So last week we talked about Docker and how we can create these containerized environments, how we can create a Docker image and then move that image from one system to another. We can push it up into a repository and pull it down to another system. Docker containers are becoming a very standardized way to move applications from one system to another. It's become a very common packaging mechanism for applications. It's also becoming a standardized way to actually run applications in a testing, development, or even a production type environment. And tonight, all of the things that we'll talk about are concerns that you would have when you're trying to scale these applications, when you're trying to scale these containers into a larger environment where you might have dozens, hundreds, maybe even thousands of containers that you're trying to manage. Now, how do we do that? That's the central question of our lecture tonight. So we'll start out by talking about service discovery. And the reason we talk about service discovery first is because it's a major challenge that you face when you begin to scale applications, really in any sort of environment. Then we'll talk about container orchestration. We'll look at 3 different platforms that organizations are currently using today to scale containers and to orchestrate containers. We'll spend most of our time looking at Docker Swarm, and we'll actually spin up a complete Docker Swarm cluster, and we'll exercise that cluster tonight during a hands-on session. So each one of you will have the opportunity to work with a Swarm cluster tonight if you so choose. And then we'll finish the evening by talking about the final. And I'll address any questions that you have regarding the final next week. So service discovery. What is service discovery? Basically, in a nutshell, service discovery is a mechanism that a service uses to locate another service. That's all it is. Service A needs to find service B. And it addresses this central question of how do we sort of wire up services? How do we connect services together in a highly distributed application? An example might be you stand up a database service in your application. And then you have maybe a set of web servers that need to talk to the database service. Well, when you launch those web servers, how do those web servers know where to find the database server? That's what service discovery is. It's answering that question. How do the web servers know how to find the database server? How does service A know how to find service B? This becomes a big challenge when you're dealing with a microservices environment, which more and more companies are moving towards. Now, if you only have 2 services, I have a web server and a database server, this is kind of an easy question to answer. But if I have dozens or hundreds of services, this becomes much, much more challenging, especially when you're talking about services that move around, services that are very transient or dynamic. And you're talking about running services on an elastic platform like a cloud computing platform where you can spin up more instances using an auto-scaling group. So you can expand and contract your services. Your services are constantly changing, maybe even moving around, as we'll see tonight in a Docker Swarm cluster. So that the services that we're talking about aren't real fixed. Their locations aren't necessarily always known. In a microservices architecture, we might have to deal with the failure of a portion of our architecture. Maybe we'll lose an availability zone. Maybe we would lose an entire region. our platform has to be self-healing and fault-tolerant, and services need to be able to reconnect with one another, even in a situation where there's part of the infrastructure is failing. We might need to update our application. We might need to roll out new updates. As we roll out new updates, we'll have services that are running. Well, we might have a service that is running using multiple versions of the service simultaneously. We might have to route requests differently within our architecture based upon the availability of services, based on the versioning of services. So there's really three methods that we'll look at, three ways to approach this service discovery challenge. The first one is a very traditional approach. The traditional approach is we just simply hardwire in all the service locations right into our application. Very simple. If I have a web application, then I would just do something like this. At the very beginning of my application, I would set, a var, a variable, and I'd say db equals, db mydomain.com. There it is. It's just wired right into my application. So when my web application starts up, it has this variable set, and that variable tells the web application where the database server is located. In some cases, this isn't a domain name, this is an IP address. It's like a fixed, hardwired location. And this type of mechanism is fine when you have application infrastructure that doesn't change very often. We always know that if we always know that the database server is going to be located at this particular endpoint or IP address, then we can just sort of hardwire it right in. And that's the service discovery mechanism we're using. We could use the outputs from an infrastructure definition tool, something like Terraform. We could use its outputs to describe, use those as a service discovery mechanism. Or CloudFormation. When you run a CloudFormation template, you can specify a set of outputs from that template, right? And those outputs could be the IP addresses of EC2 instances, or it could be the fully qualified domain name associated with a load balancer. It could be the endpoint for a load balancer or RDS database. Our infrastructure definition tooling then can provide that sort of service discovery mechanism. It's keeping track of the infrastructure resources that are being created within our cloud computing environment, and we can use that data that's stored by that state that is stored by the infrastructure definition tooling, and use that to kind of wire up the different services in our application together. The problem with that approach is that if I run something like Terraform will go out and it'll build an environment, or it will update an environment. And Terraform will maintain the state of that environment, and it'll store it locally in a big JSON file. And so after the infrastructure definition tooling runs, it provides me with a snapshot of the state of my infrastructure. But what if my infrastructure breaks at some point? An EC2 instance fails, or an availability zone fails. The infrastructure definition tooling knows nothing about the current state of the infrastructure or the ongoing state of the infrastructure. It's just giving me a quick snapshot from a point in time. So whatever service discovery information it gives me could become quickly outdated as the topology of my infrastructure changes over time. The third way to do service discovery is to use an actual service discovery platform, some sort of mechanism which tracks the location of all of my services in a much more dynamic fashion. And that's what we're going to look at here more closely tonight, is different ways or different service discovery platforms that we can leverage within our environments. How do these platforms work? I think this diagram gives a pretty good example of how most of these service discovery platforms operate. Here's an example where we have 3 different services. We've got a catalog API, an order API, and some sort of user interface. When the catalog API starts up, one of the first things it does is it reaches out to this service discovery platform and it registers itself and says, here I am, I exist, I'm a catalog API, this is where I'm located. It provides that then to the service directory, the service discovery platform. The orders API does the same thing, it registers itself. And then the UI comes along and it says, oh, well, I need to contact the orders API. Where's the orders API located? So it asks the service discovery platform where the orders API is located. It gets a response back, and then it can communicate directly with the orders API because now it knows where that service is located. If the orders API fails, or if it restarts, then it will re-register itself with the service discovery platform. So this is kind of like the central directory. It's keeping track of where all of these services are located. It's keeping track of the set of endpoints. When I say endpoints, I'm talking about fully qualified domain name or IP address, where these services are located on the network. Make sense? Seems pretty simple, right? Every service just registers itself with the central directory, and then other services can query the central directory to find one another, basically. It turns out that this service directory, the centralized directory itself, is not as simple as it first appears, especially because we're dealing with a distributed environment. And I'll talk about how we can maintain state in a very resilient manner in a distributed architecture using the service discovery mechanism. So with traditional service discovery, I mentioned that you could use something like this. Just set a variable to a domain name. Domain name services we commonly use. Domain name is a form of service discovery. It is a directory, right? It's a directory which maps a human-readable, fully qualified domain name to a machine IP address. As humans, it's easier for us to remember a domain name than it is, a set of numbers. So we can leverage DNS services as a service discovery mechanism of sorts. DNS is old, right? It's I don't know exactly how old. It's at least 30 years old. I remember using it back in the late 80s, early 90s. And I'm sure it predates that point in time, so it's at least 30, 40 years old at this point. It was really never designed for highly dynamic cloud services. DNS was designed for services and endpoints that rarely change. Not infrastructure that might be very transient and infrastructure that might exist for only a few seconds. DNS was never designed to handle that sort of use case. On Unix systems, we can define, we can map port numbers to service names on a system in this SEIS services file. That's another sort of service discovery mechanism that you'll find on Unix systems. And distributed systems, especially like file systems and databases, we leverage what are called lock servers, oftentimes, to store state, to store data. And lock servers leverage what's called a leader election process. And I'll explain what that means here shortly. So lock servers. Lock servers, it's a mechanism, and it allows a group of servers to coordinate with one another and store data, store common data, store shared data. And this is a pretty challenging problem, as it turns out. If I have, let's say, two systems, let's say I have one database server, and I have one client system or one user system, and the user wants to store the number 2. All it needs to do is contact the one database server and say, okay, store the number 2. That's pretty easy, right? But it's not very resilient. If this server disappears, now this user can no longer pull any sort of data or any sort of information, stored information, right? So we would prefer to build a more fault-tolerant architecture. So why don't we store our data on 2 database servers? That way, if one of them fails, we can get our data back, right? So now this user talks to the servers and says, okay, store the number 2 on those servers. Makes sense, right? Well, what happens if there's a network problem and suddenly one of those servers is partitioned? Now the client can no longer see that server. And the client says, well, actually, I want to store the number 4. And this says, okay, I'll store the number 4. And then meanwhile, our partition, our network comes back. This server is storing 4. This one is storing 2. Another client comes along and says, oh, well, I want to retrieve the value from the database. Which one should I retrieve it from? I'll try that one. It retrieves the number 2. I think you're beginning to see some of the complexities involved. Now pretend we don't have 3 servers, we have 5 servers. You can start to see how these partitioning problems can sort of magnify themselves. One of the ways we start to deal with this problem is by electing a leader. So these group of servers, amongst themselves, they decide to elect a leader. One of these database servers will be the leader. And there's an actual protocol that they use to do that, which we'll talk about in a minute. So one of these servers is now elected the leader, and it requires a quorum. So 3 of the 5 servers have to agree on the leader. And once 3 of the 5 servers agrees that they picks a leader, then the future communications then go through the leader. And the leader then coordinates the synchronization of data with other systems. If the leader goes, and let's say they're all storing the number 2. If the leader goes away, then the remaining systems will elect a new leader. They'll pick another system. Now that's the leader. And if this system comes back, then it rejoins the cluster, but it's no longer the leader of the cluster. It's just another member of that cluster. And it will synchronize then with the other systems and update its data so that it maintains the same state with the other systems. So when we deal with storing data in a service discovery platform, we're generally storing data in a cluster of systems that are highly available, that are fault tolerant, and that are all synchronizing their state with one another so that they're all presenting the same information to the users who are making requests for information. And this would be important from a service discovery standpoint because you wouldn't want to have two different databases in your service discovery platform presenting a different endpoint for the same service. They all have to agree on what the endpoint is. By the way, does this sound familiar? This whole partitioning and availability and consistency issue? It goes back to the CAP theorem that we talked about earlier this semester. And this is one of the trade-offs you'll find is that, again, you can't have both consistency, availability, and partitioning simultaneously. We'll look at here, we'll see shortly how that particular trade-off comes into play. So lock servers, very, very common mechanism that we use to share state in any sort of clustered or distributed database environment. The way that these servers elect a leader is using what's called the raft algorithm. And there's actually a really interesting visualization online that I encourage you. I should have linked a URL to this because it's really cool. I encourage you to take a look at it after class at some point. Just look up raft visualization and you'll find it. And it kind of steps you through exactly what happens or how systems go about electing a leader using the raft protocol, or the raft algorithm, excuse me. And it's actually a very simple and effective algorithm, and you'll see it very commonly used in these sorts of distributed platforms. So the first service discovery platform we'll take a look at tonight or talk about real briefly is Apache Zookeeper. This one's been around for a number of years. You'll find it commonly implemented in platforms like Hadoop. So if any of you have taken the Hadoop courses here, generally Apache Zookeeper is used as a service discovery mechanism. It's not something that, if you're exercising Hadoop, it's not something that you would be interacting with directly. The Hadoop platform, the different server and worker components of the platform are all communicating with Apache Zookeeper to find one another and to communicate with one another. Zookeeper is basically, it's pretty simple. It's just a distributed key value store. That's something you'll see commonly with most of these service discovery platforms. Most of them work like a key value. So you set a value in the service discovery platform. It's stored as like a hash, and then you can just query the service discovery platform, provide it the key, and that service discovery platform will respond with some sort of value corresponding to that key. That's Apache Zookeeper. Another common service discovery platform is etcd, and it's a little newer than Apache Zookeeper. Apache Zookeeper tends to be a little bit cumbersome to work with. a little more challenging and a little more complicated. etcd, on the other hand, is very simple. Very simple platform to work with. It was developed by the same team that has developed the Core OS platform. It's written in the Go programming language. So if you're a Go programmer, then etcd might appeal to you. It's also very commonly used alongside Kubernetes, the Kubernetes container orchestration platform, which we'll look at briefly tonight as well. etcd. And my goal isn't, for you to like understand obviously all the working details of these platforms. I just want you to understand in a general way, and so that if you hear somebody talk about etcd or Zookeeper, you recognize that, oh, okay, that's a service discovery platform. That's all you really need to know, in this particular course. Console. So Console is the third platform, service discovery platform, and one that we'll look at in a little bit more depth than the other ones. Console was developed by our friends at HashiCorp, which by now is probably a pretty familiar name to you. We've looked at a number of HashiCorp tools in this course, starting with Vagrant. We looked at Terraform. We also looked at Packer, a number of tools that they have developed. And they've also developed, of course, their own service discovery platform as well. Console is a service. You install it. It can run both as a client or as a server on a system. You can run it on any Linux system. I have it installed on my Mac. I'm not sure if it runs on Windows or not. I wouldn't be surprised if there was a Windows version available. Like some of the other service discovery platforms, it serves as this distributed key value store. So pretty simple, straightforward mechanism. Again, you run it in a cluster type of system. If you're working with these service discovery platforms in a sort of a testing or development mode, then you might just spin up one node. You might just have sort of one instance of the service discovery platform running. However, in production, you would never want to have just one instance. What do you think that is? Single point of failure, exactly. It's a big single point of failure. If you lose your service discovery mechanism, then you can no longer, if you lose that one server, that one node, then your entire service discovery mechanism disappears. And that can be very problematic for your application. Also, in a production setting, you would generally never run two. Why wouldn't you run two? Because you can't get a quorum. How can two people ever agree on who should be leader, right? When they both want to be the leader. That takes three people. So in a production setting, you would want to run 3 nodes or 5 nodes or 7 nodes, etc. You want to run some sort of odd number of nodes in a production setting. In something like AWS, what you would do is you'd have multiple AZs. So you have AZ1, AZ2, AZ3, and you would put one node in each of those AZs. What if you want to run 5 nodes? Then you'd double up in one of those availability zones. Where it would be a problem is which I've seen some companies do, is they'll say, oh, we don't need 3 AZs, 2 availability zones is enough for us. And they'll put 3 nodes in one AZ and 2 nodes in the other. This is a problem, right? Because if you lose the second AZ, you lose 3 out of your 5 nodes, you can never have a quorum then. A quorum means a majority. You have to have at least 3 nodes that are running at any given point in time to elect a new leader. So this could lead to a service issue if they lost an entire availability zone. Back to console. So console is this key value store. Console is also aware of the services that are registered in the service discovery database. What console can do is that it can actually perform health checks to see if various services are healthy or not. And if a service is healthy, then the service stays within the sort of like service directory. But if console detects that a service is unhealthy, then console can automatically remove that service from the directory and sort of reroute requests around it. It sounds kind of like load balancing, but we're not talking about a load balancing mechanism here. Console isn't doing that sort of distribution. Console is just checking the health of the services in the directory, and if it sees that a service is no longer healthy, then it proactively removes it from the directory so that other services don't try to use it. And the other services won't be able to use it because they won't be able to find it, basically. And then in terms of interacting with console, you can interact with console using both an HTTP mechanism, which is a RESTful API mechanism, or you can also use a DNS interface. Console actually exposes itself almost like, well, just like a DNS server, basically. So you can query services on console as if you were querying services on any other DNS server. I'll show you an example of what that looks like. So in terms of the console architecture then, if I'm standing up in an environment, what I would do is I would install console on all of my servers, all of my application servers in my environment. And I would run console in an agent mode on all of my systems. And then I would also stand up a fleet of servers, and I would install console software on those servers, but run it in a server mode on those systems. And the server mode then forms the actual cluster, where the key value information, where the state is stored in a highly fault-tolerant, resilient fashion. My systems that have the console agent installed on them, that console agent will communicate with the central console servers to set and retrieve information on those systems. Here's kind of a basic diagram of how console is laid out. So I have, for example, in one data center, I might have 3 systems. I installed a client on each of those systems. Those clients can communicate with the servers. And I can also set up console in multiple data centers and actually forward requests from one data center to another. I won't get into that functionality too much, but that's certainly possible. These clients actually exchange information with one another as well. And they exchange information with one another using what's called the gossip protocol, which is a really common protocol. And it's a way that systems in a highly distributed architecture can rapidly exchange information with one another. And there's like lots of people have done their sort of PhD thesis focusing on this problem of convergence. How does information converge in a highly distributed networked environment? You could go sort of system by system and in sort of synchronize information, or you could tell one server a little piece of information, and that server could tell two other servers, and those two other servers could tell two other servers, and so on. And you have this sort of geometric expansion of information. That's sort of the basis of this gossip protocol, is that information is just sort of disseminates rapidly through a highly distributed environment, just by servers that are gossiping with one another using the gossip protocol. Any of the data that is written to these servers that are clustered in console, that data is strongly consistent, which makes sense because, like I mentioned earlier, you would never want to have a case where the data was eventually consistent. You would never want to have a scenario where one service is looking for the location of another service and gets a response. Another service looks for the same location but gets a different response. That service discovery mechanism needs to be strongly consistent, meaning that the same value has to be present on all of the nodes in the cluster at all times. In the case of console, and this is true with most of these service discovery platforms, what they do is they decide to make this sacrifice. And this goes back to the CAP theorem once again. They decide that that they're going to sacrifice availability in the name of consistency. So they're going to prioritize consistency above all else. What does that mean? Well, it means that if there's a network partition, let's say, like in this example, if I lose this availability zone, I no longer have a quorum. I have a partition, essentially, now in my cluster, because 2 systems are available and 3 are not, at least from the perspective of the user. What console will do then is that it will automatically switch to a read-only mode. You can read data from the servers that are available in the cluster, but you can no longer write new data to the cluster. It's read-only. So that's what I mean by saying that we sacrifice availability. We sacrifice the ability to make updates. That's what we mean by availability. We sacrifice the ability to make updates to the cluster because it's now partitioned. And console is doing that to protect the service information in the platform. If these systems become available again and they can rejoin the cluster, then you can continue to make updates to that cluster. Does that make sense? Does that seem like a logical choice to make, to sacrifice availability for consistency? I think it does in this case. There might be other cases where it's not so, it's not such a big deal. If we're talking about like our Facebook images or something, I mean, it's like, who cares, right? But service discovery information, this is really important information. If the service discovery information is incorrect, then our application can fail spectacularly. Here's an example in console where a system that's running a console agent is registering a new service. So this is an example of like a web server. I have an instance, an EC2 instance. I've got the Nginx web server installed on that instance. I've also got the console agent. The instance starts up, and the first thing it does is it sends this service request, or the service registration, to one of the console servers. So it's saying there's a new service. It's called the web server service. And we're going to give it one of these tags. It's tagged with Nginx, and it's running on port 80. So the console agent sends that to one of the console servers, and then this service registration, then that information is distributed amongst all of the console servers. And so it's consistently written to all of those systems. Then any service that needs to access the web server can make a request to the console server and ask, well, where is the web server located? There's two different examples of how a service might do that. One example is by using DNS. So this is an example of using what's called the dig command, which is kind of simulating a name service request. It's sending a request. The key here is to look at this domain name, webserver.service.console. What console is doing is it's kind of creating its own DNS namespace. And any service that's registered in console will automatically appear as like a new host name as part of that fully qualified domain name. So if I send a request to webserver.service.console, then console will respond back with the IP address and the port that service is running on. Here's another example using HTTP and using the RESTful protocol that's made available by the console server. Again, doing the same thing. It's making a REST request to the console server asking where the web server service is located. And now I can programmatically use that information in my application. Instead of hard coding this variable domain name equals db.mydomain.com, my application, the first thing it would do is when it starts up is it would send a REST request to my console server and say, where is the database server located? Take whatever the response is and then store that in the variable. And now my application will use that going forward to communicate with the database server. You can begin to see then how we can sort of like dynamically wire applications together. We don't have to be very prescriptive anymore. I don't have to tell my web application exactly where the database is going to be located. Because maybe I'm going to launch my web application in 5 different environments. I'm going to launch it on my desktop. I'm going to launch it in my test environment. I'm going to launch it in my automation environment, my user acceptance testing environment, and my staging environment. I'll throw a 6th one, and I'll launch it in production. So I'm launching the same application in multiple environments. And every single time I launch an application, it needs to reconnect with other services somehow. Yeah?
But the application needs to know where the console server is.
Are you talking about like a chicken and egg problem here?
Yeah.
This is true. Yep. It does need to know where the console server exists. Correct. So generally, you have to have some sort of bootstrapping mechanism in place to be able to find the first service, right? So you might hardwire in the location of your service discovery platform, but then use the service discovery platform to dynamically find everything else. So that's commonly what we would do. And when I say hardwired in, I mean you present the, what we would typically do is we would set up something like an ELB, elastic load balancer, with a fixed endpoint, and that would be pointing to all these instances. And instead of pointing at our server at a specific console server, we would point it at that elastic load balancer endpoint, which is a fully qualified domain. Once it finds the console server, then it can start asking the console server where all the other services are located. That's a very good question, good observation.
Just in a single point of failure.
Well, if it's an elastic load balancer, it's not, because those are clustered. Now, if I'm running this across multiple AZs, I don't have a single point of failure any longer.
The cluster DNS or something, right? Then, because choosing DNS, you're still gonna have a name.
Yep, the name servers are fault tolerant as well. Right. There's no single point of failure there. But you do have to point it at something initially so that it can find everything else after that. Here's an example. I mentioned that console can perform its own health checks. Console can check the services that are in its directory to understand if they're still available or not. Here's an example using that web server service where console is actually running a shell script command, curl localhost. So it's just checking port 80 basically. See, is there a website responding or web server responding on the local host? And it's checking it every 10 seconds. If this little script were to fail, then console would mark that service as being unavailable, and it would no longer present it in its directory. If another application came along and said, "Oh, what's the location of the web server service?" then console would respond with, not found, basically. That service is not available. Now, if I'm just running one web server, that's probably a problem. But I'm, more likely I'm running a set of web servers. I'm running multiple web servers. What that means is that console will no longer respond with the IP address of the particular web server that's not available anymore. Very similar to something like an elastic load balancer. In fact, you could use this in lieu of an elastic load balancer in many cases, especially when we're talking about sort of internal services where one service needs to talk to a set of services located somewhere else in the distributed architecture. You could put a load balancer between the two and distribute requests that way, or you could use console as a service discovery mechanism, and console will hide servers that are failing so that they're no longer discovered. I also mentioned that besides just registering services with console, you can actually use console to store data. It's a fully functional key value store. Why would you want to store data in console? Well, you might store just general configuration information in console. Maybe there's a set of parameters, a set of values that you need to, different application components need to share. You could write all those values into each one of your sort of applications, or you could just put those values and store them centrally in the service discovery platform, and then your applications could reach out to the service discovery platform and then pull down all those sort of common configuration values. Very common mechanism. Here's an example of how you do that in console. If I want to get a value from the console store, I use this console. This is a command line application. I just say console KV, which means key value, get, and here's the key that I'm providing. I'm looking for console to provide a value for that key. If I want to insert a value, here's an example, console key value put. Here's the key, and the value is 1. Very simple. And you can also delete and update values from the console key value store as well. This is how you do it from the command line. You can also do this using the RESTful API as well. So you can do it programmatically in your application. That is console. Very, very common service discovery platform. I would say in the marketplace, with sort of a little older, traditional, sort of enterprise-y applications, it's not uncommon to encounter Zookeeper. Java applications sometimes are more focused on Zookeeper. I encounter console a lot. Many companies are using console in their environments today. etcd, I've never worked with. I know that companies that are using Kubernetes oftentimes are leveraging etcd. That's their service discovery platform. But today, when I work with customers, I'd say like 75% of them, if they're using a service discovery platform, they're most likely using console as that platform. Anybody here work with any service discovery platforms? Any ones that I haven't addressed? Active Directory, is that a service discovery platform? Kind of is, in a way. It's kind of a service discovery platform. Okay. I'll spend a few minutes here talking about orchestration, and then we'll maybe grab a break. I mentioned this word orchestration quite a bit in the course, and I don't know that I've ever specifically defined what it means. When I think of orchestration, I think of some sort of mechanism which is sort of controlling and managing the life cycle of infrastructure. It's the orchestra. If you think of the orchestra, the orchestra has some sort of conductor, some sort of mechanism which is keeping the orchestra in sync. With an orchestration platform, when you're managing a distributed set of infrastructure and all kinds of different and a diverse set of components, you need sort of some centralized way to manage the creation, the modification, and the removal of those infrastructure components. I think of it like CRUD operations, right? The create, read, update, delete operations. We need to do all that kind of stuff to our infrastructure. And in this course, we've been using a couple of orchestration tools already, right? The AWS Web Console kind of gives us access to an orchestration platform. CloudFormation, in some ways, is an orchestration platform, right? It allows us to, via a template, allows us to create infrastructure, update it, and then delete it. We've been using Elastic Beanstalk. That's another example of an orchestration platform. So the reason these orchestration platforms are important is because they abstract away a lot of work, right? If I'm an IT professional and if I've got to manage a highly distributed platform, it might be composed of of hundreds of different servers or services, I need some sort of tooling in order to manage the life cycle of all those infrastructure components. It would just be too difficult, be too error prone to be trying to do that kind of work in a manual fashion. Last week, we looked at Docker containers, and in this assignment from this last week, you had to create a Docker image and then instantiate a single Docker container running on your system. Well, generally our applications, as you are well aware of by now, aren't composed of just a single container, right? A single container is like a single process. A container is going to be running an Nginx web server, or it'll be running a database server, or it'll be running some sort of application server, or maybe it's running a logging service or something. Our typical application is comprised of dozens of containers. We could write a set of Docker commands and launch our containers on a single instance. Or we could use that Docker compose feature, which we didn't look at last week. I talked about it briefly, but you can write this. We created a Docker file to create one container, but you can create a Docker compose file to launch a whole set of containers that are all connected to one another, but they're all generally running on the same system. What we're concerned with at this point is, how do we launch dozens or even hundreds of containers into an environment, and how do we manage those? How do we manage the life cycle of those containers? How do we orchestrate those containers? We need to be able to create them. We need to be able to update them, and we need to be able to delete them when necessary. And we have to do this across a highly distributed environment that's composed of maybe 3 servers. It could be composed of 300 servers. One of the challenges you deal with is when you're dealing with hundreds of services and potentially hundreds of instances, it's hard to keep track of where everything is located at any given point in time. You sort of lose control over where the services are running, which isn't a bad thing, right? As long as you have some sort of orchestration platform, is some sort of control plane, which is managing where all of your services are running at any given point in time. That allows you then, as the IT professional, you're focused on the state of your services. You're not focused on exactly where your services are running at any given point in time. All you're really concerned about is, do I have enough capacity in my environment? Am I performant? Are my services performant? Are my customers having a good experience? So these container orchestration platforms, there's a few of them that we'll look at tonight, are all focused on helping us build a distributed environment to host containers. And not just host a few containers, host is really potentially hundreds of containers. And with that being said, let's take a break. We'll do a 15-minute break. And we'll take a look at 3 containers. But before you do the break, in preparation for the hands-on segment, if you'd like to spin up a Docker Swarm cluster, I think now would be a good time to do it, just because it takes a little bit of time for the cluster to spin up. So I'm going to fast forward real quick and give you that URL to spin up the cluster. And I'm going to do it right now as well. This is a CloudFormation template I created, and actually it's a pretty sophisticated template. It took me 3 days to build it. The company I'm working at is actually going to be using Docker Swarm for a new production application that it's currently building. So they gave me the time and the resources to invest in building this sort of template.
You can leave those around after class if we go back and grab
Yes.
one of those. Are they going to still usually be out there?
Yep, it's in the, well, it not only is it on S3, but it's actually in the repo. So I just copied it in S3 as sort of a shortcut for folks. I'm going to create a stack. How many people are going to do this tonight? Raise hands. Okay, great. Fair number. So go to create a stack and, oh, I didn't need to do that. You can just paste in the S3 URL. Click next. Stack name can be whatever you'd like it to be. I'll explain what some of these parameters mean after the break. For now, all you need to do is provide your key name. And for Swarm initiator count, leave that at 1. Swarm manager count, leave that at 2. And then worker count, I'm going to set that to 3. This template will spin up 6 EC2 instances for the cluster. And then the seeder address at the bottom, the network address, you can just leave the way it is. Click next. Click next. And then before you click create, you got to make sure you acknowledge the fact that the template is actually creating some IAM resources. Click create and let it go do its thing. It'll take maybe 10 minutes.
Where's the URL?
It's in the presentation, but it's also right there.
Page 35.
After you've got your, after you launch it, then go ahead and take a break, and we'll regroup at 7:20.
This is how you have to do like kind of like the email as a maintainer, email and email.
So those of you who have launched the cluster, how many has it failed for you? There were a couple failures. Yours failed as well? All the other ones have completed? I think there's a, so that the cluster requires 3 availability zones, and if AWS, and I don't know, which availability zones are going to be available at any given time. That's a query that's done dynamically with AWS. You say, okay, I want to launch this stack in this region. What are the availability zones in this particular region? And AWS dynamically spits back a list of availability zones. If it doesn't provide you with 3, then this particular stack will fail. And I think that's been a problem for some folks. If you tried to launch it in the US East 1 region in North Virginia, then try to relaunch it again, but launch it in Ohio, in US East 2. So I think maybe we used up all the available capacity in US East 1 or something. I'm kidding, sort of. I always wonder, like, is there some dude at AWS who's like, why are all these, similarly looking stacks launching simultaneously in 20 different accounts? And it probably seems very odd. Probably seems very, very suspicious. Okay, so we were talking about container orchestration. We'll look at 3 different platforms, 2 of them very briefly, and then we'll spend most of our time looking at Docker Swarm. The first one we'll look at is Elastic Container Service, ECS. This is a platform that's built into AWS. Surprise, surprise. Amazon has their own container orchestration capability. ECS is really a service that runs on top of EC2. Amazon leverages EC2 instances for each of the nodes that it creates as part of an ECS cluster. And I use the term cluster sort of loosely. ECS is more of a basic Docker hosting service than some of the other container orchestration solutions that we'll look at tonight. Certainly it's way more basic than Kubernetes or Docker Swarm. You could go to AWS and spin up some EC2 instances, install the Docker engine on them, like we did for this last week's assignment, and then deploy your containers on each of those instances. And just do it sort of in a manual fashion. ECS is managing some of that process for you. So with ECS, what you can do is you can create a container or create an image and tell ECS that you want to deploy this image on a host. ECS then will automatically spin up an EC2 instance running the Docker engine. Amazon will sort of manage that EC2 instance for you, and then they'll deploy your Docker container on that instance. I mean, it's pretty basic, pretty straightforward process. The containers that it deploys, it doesn't do it with any sort of great level of sophistication. One of the advantages of ECS is that because it's an AWS service, it can tie into other AWS services fairly gracefully. Services like Elastic Load Balancer. The ELB service knows how to connect to containers that are running on ECS instances. So there's a nice level of integration there. But again, this is a very basic, very, very simplistic sort of service. There's another piece to ECS that's called ECR, AWS EC2 Container Registry, the ECR service. ECR is basically like Docker Hub. If you want to stand up a private Docker image repository, then you can use the ECR service as your like corporate Docker repository. And again, obviously it integrates nicely with ECS. With ECS, you can say, I want to spin up 2 copies of this particular Docker image, and that Docker image is stored on the ECR, the EC2 container registry, and it all just works together very nicely. Instead of pulling your images in from Docker Hub, like we did this last week when we pulled down the Nginx container from Docker Hub, that image can be pulled down from ECR. Why would you want to use ECS? You would use ECS in lieu of sort of manually creating your own container hosting instances. And because you want to tie in your containers with some other EC2 or AWS services. You want to take advantage of some of the integration capabilities. But again, as you'll see, as we compare and look at some of these other cluster services, ECS is very basic compared to some of those other services. I think that's going to change over time. It'll be interesting to see what Amazon does with this particular service, but I'm sure they have plans to make it much more robust and sophisticated. This isn't to say this isn't production ready. I know companies who are running production services on ECS today. It's just not a very sophisticated platform. Second platform, Kubernetes. Kubernetes is it's a container orchestration platform that was developed by the good people at Google, and that was actually designed around their own internal container management process. So they kind of in a way, open sourced the process by which they use to manage their own workloads internally. And these are the kind of processes that support millions of Google services running around the globe today. The name Kubernetes is actually a Greek name. I didn't know what it meant until I actually created the slide this last week. But apparently it's a Greek name, and it means helmsman or pilot. So it's, again, this idea of orchestrating. You're the conductor, you're the pilot, you're the helmsman that's sort of guiding the life cycle of all the containers within a highly distributed pool or cluster of servers. Kubernetes then is this software layer, it's this abstraction layer that we use to manage the containers that are running within a clustered environment. Sometimes you'll see Kubernetes, by the way, you'll see it referenced like this. People will reference it, they'll say K8S. That's the shorthand name for Kubernetes. It means K, 8 letters, and then S. K8S, Kubernetes. Oftentimes you'll see that. So within a Kubernetes cluster, you'll find a master instance, one or more master instances, and then you'll find one or more nodes within a cluster. So at least one master instance and one node instance. But as I've shown you before, in a production setting, you're going to have obviously multiple masters and multiple nodes in any given cluster. The master node is the part of the system that handles all the coordination of activities within the cluster. So it's scheduling the different work on each one of the nodes. It's controlling where each one of the containers is running within the cluster, and it's keeping track of where those containers are running. Each master runs the Kubernetes server software, and then each node runs something called a kubelet, which is kind of like the fancy name for an agent. So each node in the cluster is running a small software agent. And this kubelet software agent on each node then is communicating with consistently with the master. And it's receiving updates from the master, and as the master schedules different work to be performed on each one of the nodes. Here's a diagram showing a basic Kubernetes cluster. In the middle, we have a master instance And this master instance is surrounded by 3 different nodes. Each one of these nodes, this is kind of hard to see on this screen, but each one of these nodes is running a kubelet, this little agent software package. As an administrator of the Kubernetes cluster then, what I'm doing is I'm creating application deployments. And each application deployment defines what kind of application container I want to instantiate. Like this last week, we created an Nginx application container. As part of our application deployment, we would say, I want an Nginx application container. And then I would also specify how many copies of that container I want to run. Because I might not want to run just one Nginx container. Maybe I want to run 5 of them or something. And I want to load balance my requests across all of those application containers for high availability and fault tolerance and performance reasons. Once I specify, or I create my application deployment, what Kubernetes will do is it will create something called a pod. And this is sort of an abstract concept. A pod is just the way that Kubernetes organizes the application. So it puts every application deployment inside a pod, and a pod contains everything needed to support that application, including any sort of shared resources, things like volume mounts that the application depends on. And then finally, we define a service. And what a service does is a service will expose a set of pods to the outside world. Because when we create a pod within Kubernetes, by default, this pod is it's a set of, it's an application deployment, a set of applications that are communicating with one another, but they're only communicating internally. They can only communicate with one another inside of the pod and inside of the cluster. They're not talking to anything in the outside world or anything on the internet. If we want to expose an application within the pod or within the cluster to customers on the internet, then we need to expose it as a service. Again, we can look at a diagram to better understand this process. So here's an example. This whole thing is a single node in this case. And this node has multiple pods defined on it. Again, a pod is like this logical construct. It's something that's this abstraction layer that's maintained by Kubernetes. Within each pod, then, we have a number of containers. Some of these containers are mounting volumes, mounting data volumes as well. Maybe multiple containers are sharing the same data volume as a way to maintain shared state. A single node could host one pod or it could host multiple pods. A pod is just this collection of applications as part of an application deployment. And then once again, here we have our management node in the middle. This management node is talking to each one of these individual nodes. Each one of these individual nodes has one or more pods installed on it. And we can specify as part of our application deployment, we can specify services and expose a service. So here's service A. Service A is pointing at this one pod. And service B is using these 3 pods, is combining them together and exposing a service to the outside world. So what you're seeing in terms of these like pods and services is sort of like a composition pattern. This is a way that we can use, this is the method that Kubernetes uses to compose applications and expose application services to customers for consumption. Makes perfect sense, right? Actually, it's a little abstract, until you start using it hands-on. Some of these concepts are hard to understand, but I think the key takeaway is to understand that Kubernetes has a master node and then these individual nodes. These individual nodes have pods on them, one or more pods on each node that's managed by the master node. And then we can group together these pods that each one of which contains one or more containers, and expose a service to the outside world. That's Kubernetes. Some of these concepts will make more sense now as we look at Swarm, and I'll focus on Swarm in more depth for the rest of the evening, and we'll play with a Swarm cluster here in a little bit. So Docker Swarm is a clustering capability that's actually integrated right into the Docker engine. When you installed the Docker engine on your node this last week as part of the assignment, you were in some ways creating a single node swarm. You just weren't taking advantage of the swarm clustering capability, but it was there. It just wasn't turned on yet. There was an actual standalone product called Docker Swarm that Docker had created in the past. So you'd go out and download the Docker Swarm engine, and you'd create a Docker Swarm cluster. But as of version 1.12, which came out late last summer, this Docker Swarm capability now is integrated right into the standard Docker engine that you download. So it's not a separate software component any longer. When you deploy a Docker Swarm cluster, you install the Docker engine on a set of nodes. And one of the nice things about Docker engine is that you use the same software on any node in the environment. So you don't have to create a separate sort of build image for a Docker manager versus a Docker worker. Because there's two types of nodes in a Docker cluster. There are manager nodes and there are worker nodes. And the other interesting thing about Docker Swarm is that when you're defining an application deployment in Docker Swarm, you do so in a declarative manner, as you'll see here shortly. So with something like Docker Swarm, what I would do is I would say, Docker Swarm, I want 5 Nginx instances. And Docker Swarm will go out and build those and deploy them somewhere in the Swarm cluster for me. And it will maintain 5 instances at all times. If a node were to fail, then Docker Swarm does its best to maintain whatever state I tell it to maintain. So I declare how my application should be deployed into the cluster, and Docker Swarm will do its best to maintain that deployed application state at all times. Here's an example of Docker Swarm. By the way, when I refer to Docker Swarm, often, and you see it in documentation and literature now, Docker refers to it as swarm mode because it's not a separate software application. It's just a different operating mode of the Docker engine. So we call it Docker Swarm mode. Here's an example of a Docker cluster. We have, in this case, there are 3 manager nodes. These manager nodes control all of the activities within the cluster. And the manager nodes maintain state within the cluster as well. They act as that sort of key value store, that distributed database store. And they elect a leader. They use the Raft protocol, just like the service discovery tools that we saw earlier. So they elect a leader, and they will share information in a strongly consistent manner. Those managers then talk to a set of workers. And you see, what do we see? It's like 7 worker nodes here. So you have manager nodes, and then you have worker nodes. What does the swarm manager do? Well, the swarm manager is the coordinator. It manages all of the activities, schedules all of the activities within the cluster. It monitors the cluster state, the topology of the infrastructure. If it sees a node fail, then it will automatically reschedule applications and tasks somewhere else in the cluster. The manager also provides a service discovery mechanism. So instead of having to install our own separate service discovery platform, something like Console or etcd or Zookeeper, we can leverage some of the built-in capabilities of Docker Swarm. It can service as a service discovery platform like a Console. It's not as sophisticated, but its basic functionality it meets many of our needs. And then finally, we can use Docker Swarm to perform rolling updates of our applications. If I have a currently deployed application in my cluster and I want to upgrade it with a new version, I can tell Docker Swarm that I want to update my application to the new version, and Docker Swarm will automatically go out and roll out my new update, my new software update to the worker nodes within the cluster. And we'll do that tonight as part of our hands-on exercise. What does the swarm worker do? The swarm worker just basically runs containers. Very straightforward. That's the place we run containers. By the way, the swarm manager by default will also run containers. So the swarm manager can serve as a manager node and a worker node. However, in a production setting, Docker recommends that you don't run any containers on the managers, that the managers just manage. The reason for that is that if you have some containers that are exhausting the CPU processing power of the manager instance, or the memory, exhausting the memory on the manager instance, then that you could sort of inadvertently start to form partitions within your management nodes. As we saw earlier, partitions can be very problematic in this highly distributed key value store. So they recommend to keep that functionality separate. How does Docker Swarm work? It's somewhat similar to Kubernetes in that you create a service definition and you provide that service definition to one of the manager nodes. That manager node then goes off and schedules tasks on each of the worker nodes. A task means that a container is going to be launched on a worker node. And so the task specifies that what container we want to launch, and also will specify the commands to run as part of the instantiation of that container. And then you can also define services. And a service, again, like Kubernetes, is a way to expose containers that are running within the cluster, expose those containers to the outside world. I can launch a set of Nginx containers that are running on port 80, but until I expose those containers as a service, those containers are only available within the cluster. So one service within the cluster can talk to any other service on port, or talk to the Nginx service on port 80, but nothing outside the cluster can see those services until they're exposed, officially exposed as a service. One of the really interesting things about Docker Swarm is how Swarm exposes services outside of the cluster. And it does it using this what's called an ingress grid. And this is an example where we have three worker nodes, and we have a service. This is like a web server. This is like let's say it's a container running Nginx. We have this container running on 2 of the 3 nodes. So you can see the container here in this first node, on the second node, but not on the third node. I want to expose this Nginx container service to the outside world. So I define a service mapped on port 8080 in this case. And when I define that service, what Swarm will do is it will expose that service port on every single node in the cluster, irregardless of whether or not one of these containers is actually running on the node. It just exposes that port on all of the nodes. Any request that comes in then to that port, Swarm will automatically load balance it and connect it to one of the containers in the cluster. And if the request arrives at one of the nodes that isn't hosting a container, it'll still be just redirected to one of the hosts in one of the active containers on one of the other hosts. So the cool thing about that is that from a load balancing perspective, all I need to do is I can expose my service within the Swarm cluster, and I don't have to know which exact nodes in my cluster my containers are running on. It doesn't matter, because I can point any incoming requests at any node in my cluster, and I'll know that those requests are going to be serviced properly. I can then just simply take an elastic load balancer up here and point it at every single one of my nodes, and use that as a single endpoint to access any service that's running within my cluster. It's a very cool mechanism. Okay. Enough talk. Let's see some action. Who's got their cluster up and running? Who's completed? Anybody not completed or having problems with it? Okay, everyone's up and running. Cool. Before we start playing with it, this is a quick diagram that kind of explains how it's set up. And I know it looks like there's a lot going on, but it's simpler than it looks. So what this cloud stack has done is it's created a single VPC called our Swarm VPC. This VPC is leveraging 3 different availability zones. So you see these 3 groupings here. Each one of these represents a separate availability zones where we've deployed resources into each one of those AZs. Let's see. This is actually the old version. Hang on a sec. Better. I must have had that open still and hadn't. It was confusing me. I was looking at it like, that's not exactly what it looks like. Okay. Better. Okay. So 3 AZs, and then each availability zone has 2 subnets, a public subnet and a private subnet. You see that? Each AZ has a public subnet and a private subnet. In the private subnets, this is where we have all of our manager nodes. So you see a group of manager nodes that are distributed across the availability zones. So we could lose an entire AZ and our cluster will stay up and running perfectly, not a problem. And again, also our worker nodes are also distributed across all the availability zones. The black lines here signify auto-scaling groups. The manager nodes and the worker nodes are both part of each their individual auto-scaling groups. That way, if maybe this manager node dies unexpectedly, what will happen is the auto-scaling group will automatically launch a new manager node to take its place. Same thing for a worker node. So the auto-scaling groups are constantly maintaining a certain amount of capacity, a specified amount of capacity within the environment.
Is that private subnet wrong? Because it's that private subnet is the same as the public subnet for AZ1.
Yeah, I gotta update these. Good catch. Yeah, ignore the subnet numbers. They're correct in the template. I have to update this documentation. So each, and the public side, each public subnet has its own NAT gateway. And that NAT gateway, if you recall from earlier this semester, that will allow these EC2 instances in each one of the private subnets to communicate out with the internet. Because these EC2 instances in the private subnets don't have a public IP address, right? So they can't communicate directly with internet resources. They have to go through a NAT gateway in order to communicate. The last piece we have is something I call the initiator. This isn't like an official Docker term. This is something I just sort of invented. And this is a bootstrapping mechanism. So this entire cluster, it formed on its own in using this CloudFormation template. So it self-assembles. But in order to self-assemble, you need to start out with one node, sort of the first node. It gets back to your question of like, well, if a service discovery mechanism, what do you point? You got to point it at something first, right, to discover other services. Well, this is that something. The initiator node is that first node, the very first node that starts up. And the initiator node actually creates the cluster. So it elects itself as the leader and creates the cluster. And then all the manager nodes pop up. And the manager nodes know how to find the initiator node. And they talk to the initiator node. And then they also will join the cluster and say, OK, I'm with you, leader. We'll be a member of the cluster. And then the worker nodes join the cluster as well. So they all talk to this initiator node as sort of that initial service discovery mechanism to find one another. After that point, they don't need the initiator node. The initiator node is just a manager. It's the leader in this case because it's the first one, but it doesn't have any other significance. It's not relied upon from this point forward. There's another piece here which is an elastic load balancer. And this elastic load balancer is actually listening on port 80, and it will distribute any requests on port 80 to our worker nodes. So this is sort of like a service endpoint. This is, you'll see how we can use that to distribute requests to containers that are running within our Swarm cluster. Any questions?
Is that still in the private network?
The-
ELB?
It is not. No, the ELB is the ELB is associated with the public subnets. It has to be in order to route traffic out to the internet. So That's why you don't. I have it sort of connected on the edge of this VPC. It's not associated with these private subnets. It can point to these instances within the private subnets, but the ELB itself kind of lives on the public subnet side. That's a good question,
I didn't know
by the way.
ELBs have to live in the public, right?
They don't. No, you can have internal elastic load balancers that are only distributing private traffic. But if you want to set up a load balancer that is communicating out to the internet, then it needs to be on a subnet. It needs to be associated with one or more subnets that can route traffic out through the internet gateway at the top. So, as I said, this took me 3 days to create a very complex, at least for me, template. And it took me a day just to figure out how to orchestrate this initiator node and the connection and the actual building of the cluster. That piece of it involves some interesting trickery. And I encourage you to look at the template if you'd like to see in more detail how it does that. I'm making use of a newer feature in AWS. It's part of EC2, and it's a feature called parameters. If you go into EC2 and you scroll down, you'll see something called the parameter store. EC2 now has its own key value store that's baked into the service. What that means is that I can spin up an EC2 instance, and then using the AWS CLI, I can store a value in this parameter store. And then I can spin up another instance and use the AWS CLI on the second instance to retrieve or read in that value from the parameter store. So I can use the parameter store as a centralized way to store configuration information and to share data between instances. And you might be thinking, well, why would you need to do that? It's because these instances don't know each other exist. Instance A doesn't know where instance B is located. So I can't just start up instance B and say, well, talk to instance A to retrieve that parameter. Instance B has no idea that instance A exists. But it knows the parameter store exists, and it can go to the parameter store and retrieve some information. If I click on the parameter store, or if you click on the parameter store in your console, you'll see the same thing. You'll see I'm storing some values, and these parameters are being set as this cluster is being created. So, for example, I can store the worker token, and here's the value of the worker token. This is the password. When a worker wants to join the cluster, the worker has to provide this token to the manager, one of the manager nodes, and says, okay, I want to join the cluster as a worker. Here's my token. Here's my access key. So the worker, that is stored as a parameter in the parameter store. When the worker starts up, it goes to the parameter store, retrieves that key, and then can provide it to it can provide it to the initiator. How does it know how to find the initiator? Well, again, that's stored as a parameter. When the initiator starts up, it stores its own internal IP address as a parameter value. So, not very sophisticated mechanism, but it works well. Okay. So, to start exercising the cluster, we need to log in to the cluster. And more specifically, we need to log into the initiator node. Because actually, that happens to be the only node we can log into remotely. It's sort of serving as a bastion host right now. The other nodes aren't available publicly. So if you go in and you find the IP address of your initiator node, labeled swarm initiator, find your public IP address, copy that, and then we're going to shell into it. Now, when you shell into it, you'll provide your key. Oh, I'm already shelled into it. Let me do this. When you shell into it, you'll provide your key. However, instead of using the EC2-user as your username, you have to use Ubuntu as the username. These are Ubuntu servers. They're using the Ubuntu Linux distribution. They're not using the Amazon Linux distribution that we've been using throughout the course. So you have to use Ubuntu as the username. I'm just going to become the root user sudo-s. Everyone logged into their initiator nodes?
We just put the IP address.
Sorry?
To shell in, we just use the IP address.
The public IP address, yes, of the initiator node.
Yeah, I did that. It didn't.
Did you use Ubuntu as the username?
Yes, Ubuntu add.
Yep, it's got to be Ubuntu as the username. Let's see if everything is working right. So I'll do a docker node ls. If you see something like that, then that means your cluster is up and running. What you should see is with our cluster, we launched 3 manager nodes and we launched 3 worker nodes. You'll see under the manager column, you'll see that one of them, our initiator node, that's the one that's starred. It means this is the one we're actually logged into at the moment. Our manager node is the leader. There's 2 other manager nodes that are reachable. And then these other nodes, they don't say manager next to them. They don't have any labels. So that means that they're just general worker nodes. You see each one of these nodes has a host name. And AWS, the standard, you've probably figured it out by now, the standard host name is based on the private IP address of the instance. And you see all of these nodes are ready. You also see under availability, some of them are active and then some of them say drain. What I've done is I've placed the manager nodes in a drain mode, which prevents the manager nodes from hosting any containers. I mentioned before that in a production setting, you generally would not host any containers on the actual manager nodes. You can do that. By default, Docker Swarm mode will do that. But in this case, I'm sort of emulating production. We don't want to run any containers on our manager nodes, and so we place them into a drain mode. And that prevents them from hosting any containers. Okay, so let's go ahead and deploy our first service on our cluster. So we'll go ahead and we'll type in Docker service create dash dash replicas 1 dash dash name hello world alpine ping docker.com. In the presentation notes, you see this backslash. You don't have to type that backslash in. That's just a line continuance character. If you were to run this or type in this command over multiple lines, you could use this backslash, but it's not required as if you just type in everything on one line, like I've done here. Let me make my text a little bigger so it's easier to read. So what this is saying is, I want to create a service. The service is going to be named Hello World. It's going to use the Alpine Docker image. In this case, remember, because it has no namespace here, this is an official Docker image, and it will be downloaded from the Docker Hub repository. And I want to run the command ping docker.com within the container. So it's going to start up this container, and it's just going to run ping docker.com within the container. And replicas 1 says, I only want to run one copy of this container. Hit enter, and you get back this hash value. If I do a docker service ls, it shows me that it's created this new service called Hello World. There's one replica of the service, and it's using the Alpine image, the latest Alpine image. You got an error running that command? Just check your typing. You might have just mistyped something there. If I want to look at the service, I can do a docker service inspect dash dash pretty hello world. If I didn't add the pretty attribute, then it would spit back a big JSON object. So using that pretty flag gives me something a little bit more human readable. You can see I have a service called Hello World. And here's my image, the hashtag of the image. Got one replica running. Here's the command it's running, ping docker.com. Well, so where is this? We know this container is running in our cluster, but where is it running? Which one of these worker nodes is it running on? Let's do a Docker service PS hello world. PS means process. I do a Docker service PS hello world. Now you can see here's my hello world container image, and it's running on this specific node. It shows me the desired state and the current state of that container. I didn't tell Docker which node to run it on. That's its job. It figures out where in the cluster to place any service that I want to run. And as the IT professional then that's managing the cluster, I'm really focused on higher order things like making sure the cluster has enough capacity and making sure it's architected properly for high availability. I no longer am concerned about exactly where my containers are running in the cluster. That's Docker's job. It focuses on that piece. Okay, let's start do something more interesting now. We have our single container running in the cluster. Let's scale that. Let's say that instead of one container, we want 5 of these hello world containers. We'll go ahead and scale our service by typing in Docker service scale hello world equals 5. Docker says hello world scaled to 5. Now if we do a Docker service ps hello world, now we have 5 Docker containers. And you see that they are distributed across all 3 nodes. The Docker manager decided where to place each one of those containers, and it's going to try to replace them, place them in a resilient manner, in a highly available manner. It knows that I want to try to distribute my resources across the cluster. If I do a Docker service PS, let's see. Oh, excuse me, Docker. Do a Docker PS, just a Docker PS. This will show me the containers that are running on my local system. Again, I'm on the initiator system, which is one of the workers. I don't want to run containers on my worker system. This is just showing you that it's smart enough to know that it shouldn't be scheduling any containers to run on the worker instances, and there are none, as you can see. Okay, let's get rid of this hello world service. This is kind of a trivial service that we don't want to keep around, so we'll remove it. Docker service, remove hello world. And then if I do a Docker service ls, there's no services listed. It's gone. Docker's blown away all those containers that it instantiated for me. Everyone with me so far? Pretty straightforward. We're going to do something like a little bit more complicated. Now let's create a new service, and we're going to use Redis, which, if you remember way back to the earlier parts of the semester, Redis is a key value database server, a very common key value database server. So we're going to do a Docker service create. We're going to create 3 of these. Replicas 3, I'm going to name it Redis. I'm going to give it something called an update delay, 15 seconds. I'm going to specify Redis as the image. I'm going to specify the 3.0.6 version of Redis. So instead of grabbing the latest version of Redis, I'm grabbing a very specific version. This is the version of Redis I want to use for my application. Hit enter. If I do a service, Docker service ps Redis, you'll see that we have 3 container instances, each one of which is running on a different worker node in the cluster. And they're all running the same image, Redis 3.0.6. Now let's say we come along and say, I don't want to run version 3.0.6. I want to run Redis 3.0.7 in the cluster. Now, we talked about updating applications, updating distributed applications several weeks ago, and there's a couple different ways to go about doing that, right? You could do this big bang update where I have to email all my customers and tell them there's going to be a maintenance window, we're going to be down for a few hours, and I could remove all of my Redis nodes, and then start up a whole new set of nodes, right? That's the Big Bang approach. Or I could do some sort of rolling update, which is less disruptive to my customers. It's more of a zero downtime update strategy. And that's the one that we'll employ here tonight. Let's go ahead and we're going to update the Redis containers to version 3.0.7. We'll do that by typing in docker service update -- image Redis 3.0.7 Redis. And then hit enter. If I do as docker service ps Redis, you'll see that it's already updated the first one, or one of the containers. You see this little line here showing the old version and the new version. See, it's shutting down one and it's running a new one. If I keep running this ps, now you see it's done another one, the Redis.1 instance, shutting down, running a new one. So every 15 seconds, it's going to perform another update of a container. So it's going to roll out this new version to a new instance every 15 seconds. There's the third one, shutting down, updating. So I can when I created the service, I defined this update interval. In this case, I made it 15 seconds. I could have made it, 2 hours or something if I wanted to. But I'm telling Docker how quickly I want it to roll out new updates to containers within the Swarm cluster. And again, it does it sort of automatically for me, right? I don't have to go around and figure out, well, where are my containers located? Which ones are which version? I got to shut them down, and I got to start a new one in that cluster. All that junk that you would have to do manually, it's just all automatically handled by the manager. Now, if I do Docker service inspect pretty Redis, you see that it shows me update status. The state is complete. It took about a minute to update all of the Redis containers within the cluster. Let's scale the existing containers, just like we did previously with Hello World. We'll go in and do a Docker service scale Redis equals 5. If I do a Docker service ps Redis, then you'll see that it added 2 more Redis containers. And it already knows that I want those containers to be running at 3.0.7, just like the other ones. Notice I didn't specify a version. I just said scale the service. And it knows that I want that service to be at version 3.0.7. There are times where we might need to perform maintenance on our cluster. Maybe we just want to scale down our cluster to save on costs. We want to take advantage of the elasticity of AWS. So let's remove one of the nodes. Pick one of your nodes. It doesn't really matter which one. I'm just going to pick the first one, and I'm going to copy this node name. I'm going to type in then docker node update -- availability drain, and then I'm going to paste in that node name. I'm going to tell Docker that I want to drain that worker node. Hit enter, and then I'm going to do a Docker service ps Redis. You see it says shutting down. And if you look at the nodes that are active, then my other two nodes are handling all of the instances. Docker automatically started up 2 more copies of the instances for me. So it knows that I want to maintain 5 containers. I want 5 containers to be running in the service at all times. In this case, I'm telling it to drain one of my nodes, that I no longer want to use a specific node. So it'll shut down the containers running on that node, and it'll restart them on other nodes within the cluster. If I then add that node back in, so I go availability, active, and I paste in that same node that I just drained. So now that node is active again. And then I do a service PS, nothing's changed. So I've added more capacity back into the cluster, but Docker isn't going to start any, it's not going to rebalance the containers that are running in the cluster to automatically take advantage of that new capacity. So that's something to keep in mind. Just because I added more capacity doesn't mean that Docker will automatically start using it. What I'd really have to do at this point is shut down a couple of containers and then restart them somewhere else. And my understanding is that that was a purposeful design decision by Docker. They didn't want to assume that you wanted to shut down containers and migrate them into newer instances because that could potentially cause some service disruption. Okay, let's blow away that Redis service. So we'll do a Docker service remove Redis. The last service we're going to run is going to be the most sophisticated by far. And we're going to actually expose this service this time and access the service from the internet. So far we've just been playing with containers and launching them within the cluster, but we haven't really been interacting directly with the applications running within the containers. We'll change that now. The first thing we're going to do is we're going to create something called an overlay network. We can create our own sort of virtual networks within the Swarm cluster. It's one of the cool capabilities of the cluster. I can create my own overlay IP network within the cluster environment. I'm going to do that by typing in Docker network create -d overlay --subnet 10.2.0.0/24. I'm going to call this network the Pets Overlay Network. Hit enter. If I do a Docker network ls, then it lists all the different networks that are available in the Swarm cluster, and you can see my Pets Overlay Network is available there. Now I'm going to add in a key value database service into the new network I've created. In this case, I'm going to use console as my key value database store instead of Redis. I'm going to type in Docker service create --network. So I'm going to specify that this service is going to be created within the Pets Overlay Network. I'm going to give the service a name of DB, standing for database, and it's going to use the console Docker image. Hit enter. So if I do a Docker service PS DB, now you can see that it's running one container in my cluster and running console. Running the console service. Next, we're going to add our web application. And this web application is going to talk to the console server. And I'll explain how it does that here after I type in the command. Docker service create -- network. Again, we're going to launch it into the same network as the previous service. In this case, we're going to create 2 replicas. Actually, I'll do 3. Why not? We'll do 3 replicas. And I want to expose these replicas on port 80 externally. Internally, these services are running on port 5000. And I'm going to set an environment variable using the -e flag. And that environment variable is capital DB equals small db. -- name. I'm going to call this service the web service. And it's going to use this Docker container provided by some developer who's registered it publicly in Docker Hub. One of the cool things that's happening here is this environment variable. So what I'm doing when I'm instantiating these containers in this service is each one of these containers is going to be, we're going to set an environment variable called db in each one of the containers. And that environment variable, the value of that variable is going to be lowercase db, which is the name of the console service. Swarm, as I mentioned earlier, has its own built-in service discovery mechanism. When the web application starts up, it will try to connect with the server named DB. And Swarm will automatically then respond back with the location of the DB service for us. So my application doesn't need to know like which node is the DB service running on, the IP address of the service, the port. I mean, it doesn't need to know any of that junk. You just tell it, connect to the DB service, and Swarm provides it back with all the information it needs to connect. I mentioned earlier as well, when we looked at the network diagram, that there's an elastic load balancer that's actually pointed at all of these worker nodes in the Swarm cluster. And it's waiting for a service to be exposed on port 80. And once it sees a service, then it'll start load balancing requests. So let's go into EC2. If we look under load balancers, there's our Swarm ELB, and it should be pointing at 3 instances, each one of our workers. And what I wanted to wait for was the status to be in service. It takes about a minute. Once I create that web service within the Swarm cluster, then the load balancer has to perform 2 successive health checks before it sees that service as being available. And so it's now seen the service as available. It's in service. Does everybody see that in their clusters? Once it's in service, then go ahead and copy the DNS name of your load balancer, that DNS endpoint name, and then paste it into a web browser. And voila, there's our service. This is the service that's running within our Docker Swarm cluster. It's called Docker Pets as a Service, because everything's available as a service today, right? Now, how do we use this? So this is a service where you get to vote for your favorite pet. I'm going to type in my name, and I happen to like pet whales. I click on whales, and then there's a nice animated GIF of some whales. You see that it shows me which container processed it, and it shows me how many pets have been served. I can serve another pet. There's another whale, I guess. It shows me 2 pets are served. This calendar is being stored in console, that key value database. We're persisting that data in the console key value store. And you can see that the container changes because I got 3 instances. I can vote again. Like cats. Oh, is that a rat or a mouse? Cat and mice aren't supposed to do that, are they? I haven't seen that one before. You can keep hitting another one. So obviously this is a pretty trivial application, right? But the cool thing is that it didn't really take that much for us to launch this application, right? The different components, we allowed these components to like discover one another using the built-in service discovery mechanism in Docker Swarm. We didn't have to like download and copy and like run all these commands or create a Docker file. We just have our images. We tell Swarm to deploy those images. It figures out where to deploy them, how to wire them up. And expose it to the world. We just expose it on port 80, have this elastic load balancer that points at the worker nodes, and it automatically distributes our requests across all of those nodes. You can imagine where this could be a much more sophisticated, enterprise application or something supporting, thousands or millions of mobile customers. Instead of 3 instances, I could have 30 node cluster with literally hundreds of containers running within that cluster. And the management of that cluster would be no different than managing. It would be no different to manage 30 nodes versus 3 nodes. You'd use the exact same processes, the same sort of tooling. Pretty cool. I think this is like almost like magic. Personally, and this truly is, I think, the future of where applications and application deployments are going. There's no question in my mind. Like nearly every company that I've worked at in the last 18 months they're all definitely talking about this, and many of them are actively doing this now. Maybe they're starting with greenfield projects, but I know that they're thinking about like 5 years from now, this is where they want all of their applications to live in this sort of environment. Okay. So the last thing you should do is shut everything down. Unless you want a nice bill, because we've spun up a lot of resources for this little demo. So go ahead and go back into your CloudFormation. You don't have to spin it down, by the way, if you want to continue playing with it tonight, or you can spin it up again tomorrow, whatever. I encourage you to have some fun with it. I'm going to go ahead to production and just tell it I want to delete that stack. And I'll go ahead and then remove all of those different AWS resources that were spun up. I think it created something like 100 different resources for this particular stack. So this is an example of like, if you had to create this manually, good luck. It would be very difficult. You need like 50 pages to reproduce this configuration. So you can only do this using the power of automation. Okay, some final thoughts. The good news is there's no homework assignment this week. Next week is our final exam. My expectation is that it will be similar to the midterm exam. maybe, similar sort of number of questions, true, false, multiple choice. Maybe I'll throw in a small essay or something. Who knows? Or short answer. I shouldn't say essay, but I might do a short answer sort of question. The material this is not cumulative in the sense that I'm not going to ask questions specifically related to material from the first half of the semester. But of course, there are certain concepts obviously that apply throughout the course, like EC2 concepts or maybe some shell scripting concepts and so on. I'll ask, the second half, the second test in this course, generally students have found it to be easier than the midterms. Across the board, students last semester said it was easier, and the scores prove that out. I think part of that is because there's not as much material for me to test on in the second half of the semester, because we spent a lot of time talking about like cloud formation templates, Ansible, and I'm not going to test you on syntax. I'm not going to ask you what's the syntax to do so and so in a cloud formation template. That would be madness because frankly, I don't memorize all this stuff myself. I would look at documentation to find that information. I might give you short snippets of code and ask you in a general, sense of what does this code do? So I might give you, 5 or 6 lines of CloudFormation template code and just ask you, what is this doing? I'm not going to ask you to write syntax, but I want to test to see if you have a general understanding of what something is doing. Some code syntax is doing. And of course, with multiple choice, I provide you with all the answers in advance as well. So I'm not trying to trick you. One of the answers there is the best answer that's available. For the final exam, I do set a time limit. So there's a 2-hour time limit on the exam. I think last semester, the average student finished in 45 minutes at most. So 2 hours should be more than enough time for this particular exam. And we'll use terminals again. We'll just use the Blackboard system as well for that exam. If I do include a short answer question, then I won't be able to provide the automatic, scoring after the exam is done because I have to manually go in and score. So I'm debating sort of whether to do that or not. Yeah.
Can we bring our laptops this time?
I'd really prefer that you use the terminals.
Like we can go to the lab like last time?
Correct.
Okay.
Yep. And I just wanted to finish things off by soliciting any recommendations that you have for improving this course. This is the second time I've done the course. I'm scheduled to do it again in the fall. I've got some more victims who've already signed up for the class. And each one of these classes has been slightly different. The material in this class, I'm improving it every semester. I think the material this semester was better than last semester in terms of its relevancy and its accuracy. But I'm constantly looking to improve the course. So I'd love to hear your recommendations. One of the things I'm considering is flipping the course. If any of you have taken Charlie Betz's class, he runs a flipped course. And in a flipped course, what would happen is instead of coming here and listening to me drone on for 3 hours and falling asleep in the process, I would actually pre-record all the lectures. So they would be available as a series of videos each week. And so as a student, you would watch the lectures at home, on your own time before class. And then when you come into class, then each class period would be pretty much all hands-on technical work. Be exercising a set of technologies and working through a lab or working through a homework assignment, actually in the classroom here. And you might still have some work that you do on your own outside of class, but this would be like another opportunity to get sort of more hands-on with the technology. So I've never done a flipped class before, but I'm sort of toying with that idea, and I'd love to hear your feedback on whether you think that would be great or like, no, that's a terrible idea. I don't want to listen to videos or. But any thoughts?
How would that impact with like the reading assignments? Only because those two books are like industry standard ones. And
Yes.
Very important to.
So if I did that, I would drop one of the books. In fact, I will probably drop the Cloud Systems Administration book for the next semester. I love the book. I think it's great. But it's sort of like tech books are only good for a few years, and that one's like already almost 4 years old. So, yeah.
I think it's a good idea to do a hands-on, only if the labs that you work on or the class assignments, they actually work. Because I'm taking Charlie's class right now, and not most of the time, but there was instances where the labs wouldn't work, and you find students just like
Hanging out.
losing focus
Yeah.
in class. So, because sometimes the servers were too busy to kind of carry all that load, and he had to spend class time to figure out what's going on and all that kind of stuff. So much of the class time was lost just trying to figure that stuff out.
Right.
But if the labs were to work, and if you were to do what you were doing with our hands-on right now, I think that's a really good idea.
Yeah, Charlie is struggling with his use of Vagrant instances running on a single server, and he desperately wants to move everything to AWS.
Yeah. And maybe because we're using AWS, we haven't had that.
Correct. Yeah, I knew from day one that I didn't want to use, the Vagrant or anything like that. I didn't want to rely upon. I didn't want you to have to rely upon your own laptop or any St. Thomas-based infrastructure for this course. Everything is done at AWS. And that doesn't mean that stuff in AWS is perfect, but it's not a constraint, a performance constraint like that. Other thoughts?
I think that flip part sounds interesting. You can almost even, there's an idea like doing a combo where like maybe the first hour is kind of more of like a lecture or review of the
Yes.
material and then talk about that. And then, for me personally, I would benefit well from like more in class time, like at least to kind of get a start on the homework assignment and things like that. I think that's interesting.
Yeah.
You could consider, I think I mentioned this, is instead of recommending people use Putty, is that Git Bash seems like a nice tool, because once you get Git with it,
Yep.
and you get all the Bash commands and SSH stuff that we needed to really operate, and I found that to work really well
Mhm.
as an alternative. And then it's kind of the same thing you're always showing, and as you're walking through it, it's not, they have a different tool maybe.
Right.
I don't know if that.
Is Git Bash installed on the school terminals?
Yeah, I've been using it here. Yeah.
Okay, it's a good recommendation.
So that was nice too, it was all there.
Yeah, I'm personally not a big fan of Putty. It's a little bit cumbersome tool to work with. What else? What other recommendations? Pretty.
Not a recommendation, but a comment that I found this class to be the best class in my entire degree, just letting you know. This was the best class I took. This is my last semester, and I was so glad I took this class.
Who else is graduating this semester? Wow, there's a lot of you. Well, congratulations. That's really exciting. Whew, you're done, right? Well, after next week, you're done. That's a good feeling to have. I know what it takes to persist in this program. So there's kudos to all of you who are graduating. And I learned as much as all of you do in this class. So that's, the takeaway for me is that in this discipline, you can never stop learning. It's just not possible. If you stop learning, you'll quickly find yourself unemployed or almost unemployable in this industry. And I think every 5 years you need to reinvent yourself. Half of the technologies I have taught or used in this course, I didn't use them a year ago. So I had to learn them. And then I had to learn and figure out, well, how do I teach other people how to use these technologies? And so I'm sure a year from now, if you came back, you'd find that the mix of technologies that I've used and incorporated in this class have changed once again. That's just simply the nature of the business. And so I think to do well in this industry, you have to be a good learner. I think the other trait is you have to be a persistent problem solver. And I know many of you in your assignments, you encountered problems like every week, right? Some technical hurdle. And it's, in some cases I couldn't help you solve the problem. It's something I'd never seen before. And part of the challenge of, I think, working in this industry is that you're constantly confronted with problems in new situations that you've never experienced. And it's that level of persistence that you apply to your job that really helps you overcome those challenges and continue to evolve and learn in your particular discipline. So with that being said, I really appreciate all of you and your involvement this semester and getting to know each one of you. If you have any questions over the next week on lecture material, you can certainly reach out to me, email, or via, if it's something you think the class would benefit from, use Slack as a channel. And, good luck with your final next week, and good luck with all of your other finals. John?
I think for the first exam there was a study guide. Is there anything like that?
Oh,
Just so
yeah, good question. There is a study guide. I need to update it. So let me post it in the next day or two. I'll post the study guide for the second. And this last lecture is on the exam, by the way. So the material from this last lecture is on the exam. So thank you.
So